Of course he is, he has expressed his interest, and I do think that interest is genuine. So,
I mean Ben Erickson.
Oh, Ben Erickson.
Yeah.
Ah. Well, okay. I mean, I will ask him. I don't know, if he's interested or not, but
I think it's going to grad schools.
right. It would be good for him, for sure.
He's thinking masters, but still.
Oh, good grief. He's thinking masters. Oh my goodness. Yeah, I need to talk to him. All right. Let's see here. So we are now in. Well, I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for this class and this opportunity we have just to study your creation together. Help us to just understand a little bit more manifolds and how to think of them and how to construct them, Lord. In my prayer, Lord Jesus. Amen. So, all right. So, chapter 10. And this is my 2015 notes, right? I have entitled it "Calculus with Differential Forms," but it takes me a minute to get to that point. See, because I want to really take a look at how we get to. How we construct manifolds, if you will, in Euclidean space in Rn. And okay, so like what we're going to do in this chapter, among other things, is talk about like what's a submanifold of Euclidean space, what is its tangent space, what is its cotangent space, what is a vector field, what's a smooth function on a manifold, what's a smooth function between manifolds, what's the differential of a function. And so we've already talked about some of that language we've already used before. Like we talked about the tangent space, we talked about the normal space, but there we were actually thinking of it literally as, an honest to goodness subset of Rn. So we leave that perspective behind and we adopt a new perspective in this chapter where we actually think about tangent vectors eventually as differential operators. So there's an identification of the directional derivative essentially with the partial derivative, which is building the directional derivative formula, and this allows us to essentially identify vectors with differentiation operators called derivations. Now, and then that naturally leads to something called the push forward. A push forward, you can take a vector field on one manifold and you can push it forward to a vector field on another manifold. That's a natural thing. And then we'll look at differential forms. In differential forms, we'll see that if you have a function from one manifold to another, if you've got a differential form on your target manifold, you can pull it back to a differential form on the initial manifold. And the story of pullbacks and push forwards goes together. Both of those play nice with the wedge product, we'll see. And then we'll look at eventually like calculus in R3, how to do that with the exterior derivative. And then perhaps more interestingly, we'll look at the generalized Stokes theorem, and we'll eventually look at also something called the Poincare lemma. And so all of these things are, very interesting calculations, but we have to start at the beginning. So, and this is informal. All right, so this is I'm not giving complete definitions really here, but I'm just going to kind of, define for you, roughly speaking, what's a manifold. So manifold is a set, right? And it's got, charts. And so if you got like chart, I'm using chi-i apparently in here, chi-i and chi-j, right? And those are bijections, right? So like here, this would be like, oops, my bad, chi-i of the intersection. It may be this, and down here, you've got maybe this is a picture of chi j of the intersection. So the intersection of the ui and uj is where they're both defined, right? And so then you can define down here theta ij in my current language. Now here, let's see here, ui comma xi is a coordinate chart. Although the coordinate chart, the domain of the coordinate chart, of course, is the ui. And here we have that xi is a mapping from ui to rn, all right? And basically we assume that these mappings are in fact homeomorphisms, all right? Now, and in fact, there are different ways to define a manifold if we're going to be more careful. Some people start by saying a manifold is a particular kind of topological space that comes paired with this atlas of charts. Other people just think manifold's an abstract set and they use the charts to induce a topology on the set. I've seen both done in courses.
So in this area of intersection, there's a bijection from one.
Oh yeah. So this theta ij we could build as what? It's the basically like this, right? So it's the let's see here. The last shall be first. So xj composed with chi I inverse, right? That's a mapping from, chi I of the intersection to chi j of the intersection, I believe. That's called the transition function. And so for M to be a manifold, you need a collection of charts, all right, where the union of all the chart domains covers the whole manifold, and also they have to be quote unquote compatible charts. And compatibility just means that the transition functions that relate them, well, we're going to say that they're smooth. You could look at manifolds that this transition functions were just once or twice differentiable. You could talk about like a class CK manifold. You could build other structures into the transition function, like you could talk about complex manifolds. There's other things that could be done there. Well, like the supermanifolds that we talked about. So here I'm not thinking this is an infinite dimensional space. I'm thinking that this is really, for our purposes, we're just thinking M is literally some kind of subset, right? It's a subset of Rn. I don't really want to impose that on myself exactly. I mean, I might want the manifold to be a subset of like matrix space or something, right? But of course, matrix space you could identify as n squared dimensional Rn anyway. So, keep in mind I'm saying Rn with some hand waving. Depending on how literalistic you are on your math, might be needed. But the transition function for us, we're going to assume smooth, yeah, and that just keeps things nice. Especially,
If we didn't have the smooth condition, it just needs to be a bijection.
Well, it depends on what kind of manifold. Like if
we just have a general manifold.
Okay, if we're just talking about a topological manifold, then yeah, it just has to be a homeomorphism. A differentiable manifold, once differentiable, right? Although sometimes people use differentiable to mean smooth, so that's not a good example. All right, anyway. So I think now I have examples, all right? I have some examples. So example 1, here we go. M is x comma y in R2, such such that x squared plus y squared equals to 1. All right. I say the usual chart on the unit circle is just the angle chart. So how do you do that? The angle chart. Theta is kind of like chi, right? It's the chart. So given, I say given, you know, cos t, sine t is an element of M, right? We have, I suppose that's equal to P for the sake of discussion here. We have what? Theta of P equals to what?
What do you mean by angle chart equals theta equals chi?
I'm just saying in terms of my notation over here, I'm thinking the angle chart theta. What is, we already know what that is, right? I mean that, if this is the point, the angle is, you know, t. Now, admittedly, that, you know, that's only going to be a bijection if we make some certain restrictions on our choice of t, right? And this can't be a global coordinate chart for the circle because it's necessarily got an angle jump, as we've talked about with endless devotion and complex this semester, right? I mean, like, yeah. So another example. Now, I do give a formula for it, right? Like, if you want to, you could, and I'm going to change the letters here. Well, I mean, fine. I just would warn you that the way x and y are used, I'm not sure that this current use of x and y here is really is compatible with later uses of y and x in this chapter, okay? But anyway, that would be the formula for the theta chart for x greater than 0, right? Example 2, we could have m equals to r2, right? And the usual chart is just chi1 with, you know, the identity is equal to, right? You know, u1 equal to all of r2. So like, you know, chi1 of, well, basically chi1 is equal to quote unquote x comma y. Those are the component functions of the usual global Cartesian coordinate, you know, and the way those work, of course, is, so what I'm trying to say, Ernesto, is like my use of x and y is varied, and don't read too much into the, well, I say that, but I actually do want you to read things into the notation in certain contexts, so if you find me a hypocrite when it comes to the notation, then congratulations. You've joined a proud tradition of people who are annoyed with their professor's notation for differential geometry. It's a long and honored, time-honored tradition of being annoyed with other people's notation. All right, so this is one coordinate chart. Of course, we could also use the, if we let u2 equal to, let's say, 0 to infinity, Cartesian product with the reals, right? So that's the positive half plane, right? Then we could do like chi2 of AB equal to, oh, I don't know, square root of a squared plus b squared, and then inverse tangent of b over a. You might recognize this. This is r. This is theta. Natural question to ask is, are these compatible? Like what if we do chi, so that was chi2, right? What if we do chi1 composed with chi2 inverse? What's the transition function here?
Well, r sine, r cosine, theta equals x.
So what's the what's the inverse? What's the inverse? Well, first of all, what's the inverse for chi1? That's kind of stupid, isn't it? So this is very dumb, right? Chi2 of what? Chi1 is the identity map, so there you go. That's chi1 inverse, and then what's chi2 of it? Well, this is, you know, square root of u squared plus v squared inverse tangent of v over u. So that would define, in my current lingo, theta 1, 2, I suppose, of uv, right? What if we go the other way? What would theta 2, 1 be equal to? That's a little bit more interesting, isn't it? Because what is the inverse to the polar coordinate map?
X equals r
Uh-huh.
cosine.
Right. Yeah, this is a little bit more familiar, isn't it? That's, like you said, u cosine v and u sine v in our current notation, right? Which, of course, is u cos v, u sine v. Now, the interesting thing is if you look at the theta 2, 1 map, like that's smooth on R2. If you wanted to extend the domain of uv here to be everything, that's everywhere smooth, right? But you can see the necessity of that choice of chart domain more so in this formula, right? Because in order for in order for that actually to be the inverse, we do need that u is positive. And in order for this to be differentiable, we need that u is not 0, right? Which we have in this context.
And you're using theta to make two different things, right? The theta to 1 and 1, 2.
Right. Well, it's this notation over here.
That one over there, it's just...
That theta is just like calculus 2, calculus 3 theta. That's the theta from the calculus sequence. This is the transition function. Maybe I should decorate it, make it a more fancy looking theta, like this. Woohoo! There. See, now it's different. Anyway. Okay, so good news. Polar coordinates and Cartesian coordinates are compatible coordinates. Right? There's one manifold structure in R2, and our usual choice of Cartesian or polar coordinates, they're in fact part of the same differential structure. Now, the use of coordinates, at this point it's worth mentioning, in Calculus 3 and even Calculus 2, our use of coordinates is a less refined thing. Well, maybe it's more refined. I don't know, it kind of depends on your perspective of things. See, I'm going to only be talking about, at least for a long time, I'm talking about manifolds without boundary. So a manifold without boundary, it doesn't have a boundary. If you do talk about manifolds with boundary, then you also have to talk about boundary charts. And boundary charts are a little bit different. They're not mappings into open sets. These really should, my pictures aren't very good. These really should be like open subsets of Rn, all right? I didn't even decorate these. These are both Rn for an n-dimensional manifold. And I really should say that this is a subset of R big N or something, where generally speaking n is greater than big N. There's a famous embedding theorem by Whitney that says that any abstract manifold of finite dimension can be nicely embedded inside a Euclidean space, inside Rn of n sufficiently large. And then there's even deeper theorems by the mathematician Nash that give you like embeddings in which the The notion of metric, the notion of distance on your abstract manifold is in fact one and the same as the inherited notion of distance that is restricted from the ambient Euclidean space of sufficiently high dimension. That's a much more technical theorem. Both of those theorems are pretty technical. My point is that there's not really anything theoretically to be gained by supposing your manifold's not inside Rn, because theoretically it can always be proved that up to like a diffeomorphism, there's a diffeomorphic copy of your manifold inside a Euclidean space of sufficiently high dimension. So it's like, at the same time, it is convenient to think about manifolds which are not strictly column vectors. Just like same reason in linear algebra, right? That we think about abstract vectors. It's helpful. Since I spoke the words linear algebra, I should probably mention that a vector space, right? A vector space is a manifold, right? So example 3. I'm a little bit out of order here just because it came to me. So if I have M equals to V vector space over the reals, dimension V equals to N, then if you just put chi equal to phi beta, where beta equals to V1, V2, Vn is basis for V, then that single global coordinate chart, phi beta, will give you it gives you a global coordinate chart on a vector space. A vector space, especially in Russian literature, is called a linear manifold or a linear space. And an abstract vector space is really the prototype of what a manifold is. So to really understand a manifold, you need to first understand linear algebra in the abstract way.
You said a vector space is linear.
A vector space is a linear manifold. Linear manifold. And so if we had two different bases, right? If you had beta 1 and beta 2, two bases, right? Then you could define, chi 1 equal to phi beta 1 and chi 2 equal to phi beta 2, right? And so for both, the domain would just be the whole vector space, right? I mean, I'm saying you can make it that. You could make them smaller. Here's an interesting theorem that's easy to prove, although I haven't stated anything so careful as to make a proof possible. But if I had, one theorem you could prove is that anytime you have a chart domain, you can restrict the chart domain and still have a chart, because you still have all the same properties for restriction. So that's kind of cool. Then the question is, what do the transition functions look like for a linear manifold? See, we already talked about this actually. What is chi 1 composed with chi 2 inverse without loss?
Change of basis.
Yeah, I think you're right. I think it's a change of basis function, isn't it? So that's phi beta 1 composed with phi beta 2 inverse. And I think you're exactly right. I think that the picture to have in mind here is that if we've got the vector space V, well, you've got phi beta 1, beta 1, you got phi beta 2, you've got yourself Rn, you got another Rn down here, right? That's how I think of it anyway. And then this mapping here is, oops, my bad, this way, because phi beta 2 inverse comes first and then phi beta 1. So here's your chi 1 composed with chi 2 inverse, also known as what? Theta 2 1. Right? There's my transition function for a linear manifold, which, as you said, is just the coordinate change map. But more to the point, what kind of map? Is this a smooth map? Like, if I write chi 1 composed with chi 2 inverse, right, and I let it act on a general point down here, let's call it u vector. Well, the thing is, I can write a formula, a times u vector. Right? There exists a fixed matrix such that this is equal to that. Not only is it smooth, it's really smooth. I mean, it's linear, so that's very much smooth. The higher derivatives are 0. Past, like, second and higher order derivatives of this transition function are 0. It's very, very linear. It's be very smooth. I don't know how it can be more smooth than smooth, but if there was such a thing as more smooth than smooth, this would be it. I'm just talking nonsense now, but it's what I do. Example 4, we could talk about spherical coordinates on R3, right? Chi spherical of x, y, z would be, let's see here, r, theta, phi. I guess the question is, am I using math? Or am I using physics, as Dr. Scamorta says? I think I'm using a mixture. So my current definition of sphericals at this point in the notes is x is equal to r cos theta sine phi. Y is equal to r sine theta sine phi. So this is some sort of weird halfway house between, like, the sphericals. Okay, so in mathematics, what's the difference? This is almost math, actually. In math, we just typically use what? We use a rho for r, right? Here's another thing you could do, by the way. If instead you had r cos theta cos phi, r sine theta cos phi, and r sine phi, like that. Well, it's obviously a different phi, right? So if I call that phi tilde, the difference is, if you draw a picture, right? If this is the point we're talking about, first of all, to figure out theta, we sweep from the positive x-axis down here, right? And so phi is swept off the z, right? But phi tilde is swept up off the xy plane. So, like, if you read, for example, Barrett O'Neill's Elementary Differential Geometry textbook, which is a wonderful book, he likes to do his spherical coordinates like this. And I almost think it would be better for us all to do that all the time, because it makes phi tilde, well, then phi is really the latitude. Our usual math phi is maybe what we should call colatitude, because it's complementary to the latitude. This would literally be like latitude if we were to impose an Earth with the equatorial plane on the xy plane. That would be latitude 0 is the equator, you know. But anyway, and then theta is the longitude. Man, that would be nice. Well, anyway, those are other. I'm not using these. I'm just saying there are other choices here. Of course, in physics, they typically switch the meaning of theta and phi so that theta is actually phi and phi is actually theta. So it's okay. Anyway, so I don't know why I'm talking about that here. We've got more interesting things to talk about. Let's get back to the interesting things. So there's your spherical coordinate system. And it's implicitly defined by the coordinate transformations. These can be inverted, right? So these can be inverted in particular, r is the square root of x squared plus y squared plus z squared, right? Theta is inverse tangent. Now this is a lie. Okay, this has got strings attached for x greater than 0, right? And if you're willing to add a number to that, then you can say it's, you know, it's right for everything except for the y-axis, you know? Anyway, and then phi, well, phi, we can solve for phi if we look at this equation here. So it's just inverse cosine of, you know, z over r, which in this context is inverse cosine of z over the square root of x squared plus y squared plus z squared. All right. So, yeah, so if I was to, you know, the inverse, chi-spherical inverse, man, that's a really bad label, of yeah, well, that's well, whatever I want to put here. If I put ABC here, for instance, then what I would put would be, you know, oh man, I'm sorry. All of a sudden you're right. I should probably just put r theta. See, this is the danger, is we use the symbols both as a point and as a mapping. And then I get confused at times. Oh, well, then of course it's these, right? And these are actually the formulas that would go here explicitly, right? And then, of course, in R3, well, okay, so this is a coordinate system not on all of R3. Like with x greater than 0, right? So basically, it's a coordinate system on half of R3. If I'm just lazy and don't try to extend theta maximally, if I just want to use inverse tangent and not belabor the point. Now, the inverse cosine's good. That goes from minus pi to pi.
Can't we have another map?
Minus pi over 2 to pi. No, excuse me. 0 to pi. I'm an idiot. Inverse cosine. Duh. What's that?
Can we justify another mapping of the other half and then they're compatible?
Well,
that fixes the
I
main tangent.
I can't extend theta to the whole of space without having that angle degeneracy. I mean, you're right. I can extend theta to everything except for like there's got to be an angle jump somewhere. So if I do 0 to 2 pi, then the theta is not going to be a good coordinate here.
Sure.
You know?
For continuity.
For continuity. Now, since we're primarily interested in Calculus 3 with integration, losing like a plane in a volume doesn't change the integral, so it usually doesn't matter. Oftentimes you can get away with improper integrals without limits. We don't even notice we're doing it sometimes. Okay, so I think we could go through a similar calculation to the one that we did over there in terms of looking at the composition of like spherical coordinates with the global Cartesian coordinate system, right? And again, since x is positive, the derivatives of these are going to be well behaved, right? You notice, like, if you get to the origin here, this guy's not well behaved. But as long as you're not quite getting to where all three variables are 0, that's okay. This one, again, if you get to the origin here, it's a problem. So as long as you're staying away from the origin, like spherical coordinates are not technically a coordinate system at the origin. And yet we use spherical coordinates to integrate from the origin all day long in Calc 3. Because our notion of coordinate system is not the careful manifold. All right. Okay, now, this example is now we're going to leave the realm of Calc 3. Yeah, go for it. The next example I have here is, not something I would do in Calc. Everything up to this point is something I could conceivably have talked about in a Calc 3 class, more or less. I mean, I don't do this in Calc 3 usually, except April Fool's Day. But, let's talk about a circle. So, yeah, I mean, angle is natural, but there is another usual, pretty standard way to do it. And so if we have, see if I can do it. I guess I'll just draw 4 pictures. I probably shouldn't do that. All right, fine. V plus, fine, 4 pictures it is. That was supposed to be the same. All right, so I've got V plus, V minus. So V plus and V minus look like this. Here's V plus. V minus, like this. All right. And so my manifold here is just xy such that x squared plus y squared equals to r squared. I think I'm doing, did I do r squared? Oh, I did 1. Oh, rats. Unit circle it is. Although you could adapt what I'm doing for, a circle of radius r if you wanted. So basically here we have y greater than 0. Over here we've got y less than 0, right? And so this is so-called V plus. This is so-called V minus. And since obviously we haven't covered the whole sphere yet, right? We will use also this one. This will be, x greater than 0. This is your VR, R for right, and then here x is less than 0 for these points, right? And this is what we'll call V sub L. And so these are the domains for the coordinate charts, and I will name the coordinate charts through a similar notation. All right. So here's the formula. Chi plus of xy equals something. Chi minus of xy equals something. Chi r of xy equals something. Chi L of xy equals something. And so what we do is we just project out the x. So plus and minus just is defined to be x. And right and left we just define to be y. So they're just the projection maps onto the coordinate axes, right? And this gives us an atlas on the circle, which we can call the differentiable structure. And we can check that their transition functions are smooth. Let's try to work that out. Let's look at xr. Let's look at the, let's work out one of those.
By atlas, we made the collection of 4 charts.
Yes, the atlas here is the collection of all 4 charts. Now, if you want to get all fancy and stuff, you can talk about a so-called maximal atlas. The maximal atlas is when you take a given atlas and you adjoin to it all possible compatible charts with the given atlas. So a set together with a maximal atlas is usually called the differentiable structure. But sometimes we don't want to work with the maximal atlas for various reasons, so we content ourselves just to have a collection of charts whose the union of the domains of the coordinate charts covers the whole manifold, and they're compatible. And that's indeed the atlas here would be, you know, V plus chi plus V minus chi minus VR chi R VL chi L. All right. That would be, that's your atlas. And let's check compatibility. In a particular case, I'll follow my notes to keep myself out of trouble. We'll look at X, chi R composed with chi, where was I? Plus, so chi plus inverse, all right. And I'm going to look at it, I'm trying to use U and V, except that's bad because I shouldn't do that, because I should use what? Dummy. Yeah, X and Y here. I mean, you could use just U, but I'll use X so that it's more familiar. I probably would use a U there for a theoretical calculation is my point, okay? All right. So this is chi. So what's chi plus inverse? It's well, it's x comma y, right? But to be more accurate, it's x comma which y? It's the square root of 1 minus x squared, right? The reason that is because the inverse of the other one is x comma minus the square root of 1 minus x squared. That gives you the y negative. This one down here, chi r inverse. Yeah, it's exactly square root of 1 minus y squared, comma y, chi L inverse of y minus the square root of 1 minus y squared y. Right, okay. So there you go. There's the mappings. There's their inverses. Great. And so here we're looking at chi r of x comma square root of 1 minus x squared, which just gives us what? How does that one work? It projects the y. So square root of 1 minus x squared. Now this x, where is it supposed to be taken from? What's the context here? We're supposed to be, you know, like the theta plus r is a mapping from what? From like, yeah. It should be a mapping on the, well, all right, I'm trying to think here. What's VR intersect with V plus equal to?
That's x greater than 0, y greater than 0.
X and y both greater than, okay, so yeah. So it's a quarter.
Yeah.
So it's the quarter circle. So let me just draw a picture again. So we've got, here's our circle, right? And we've got, here's my V plus, here's my VR, right? The intersection is this quarter circle here, right? And so let's see here. We have whichever we want to call that. I mean, I'll call it chi plus over here. I'll call it chi r over there. And you know, basically, let's see here, chi plus, maybe I should do like this, whereas chi r, it's kind of more like this, right? If I'm going to draw it like the x versus the y, you know. And so, all right, so chi plus inverse takes an x down here, right? It maps it up to here. And then down here. Right? And so the mapping x maps over to the square root of 1 minus x is the quote-unquote theta, the transition function. I'm debating whether or not I'm supposed to write plus r or r plus. Okay, full disclosure. I forgot, because I erased my stupid convention. But anyway, the point is, given this context, we have what about x? What's the trouble here?
1x equals 1.
Yeah, so right, x equal to plus or minus 1, trouble, because you've got vertical tangents there, right? But thankfully, we have what for this? For the intersection, we have what? We have 0 less than x less than 1, right? And so this mapping is smooth. And if you go the other way, right? If you go the other way, if you start with y here, then you go what up? You go back up to what? This point up here would be what? It would be like the square root of 1 minus y squared y, right? And then that will map back down here to what? Square root of 1 minus y squared, right? So going the other way, you have y maps to 1 minus y squared, which is okay because we have what? We have 0 less than y less than 1. So every one of these overlaps, it gives you a quarter circle, and on the quarter circle, we don't actually attain the x and y being plus or minus 1, which is important because those are the places where these formulas break down in terms of their smoothness. Obviously, they could be continuously extended to the endpoint, but they're not differentiable there. Again, they've vertical tangents is what you're up against. So that proves, because without loss of generality, they're all the same, that the circle is a manifold. All right. Now I'm not cheating. There's no angle jump thing going on here. I've given you the full story. Now it's a little bit wasteful, right? I had to use 4 charts to get it, but there it is. Now there is a way to cover the circle with like 2 charts. I don't know if it's in my notes or not, but like sometimes people do this. They do something like, I don't think the formulas are quite as neat, so you can do something like just go a little bit below, like that, and then go a little bit above, like this. And so if you did that, then you've covered everything. But then the thing that gets a little bit more complicated with that choice is that when you look at the transition functions, you have 2 different cases to consider because they intersect here and there separately. But anyway, just saying. All right. Now, next example.
So So the charts in this example are mapping every point in the circle to a point in R2.
In R.
In R. Yeah, okay. So it's a one-dimensional manifold.
Exactly, the circle is a one-dimensional manifold. Yep. So you're like, I would like a two-dimensional manifold. Well, coming up. So if we let P, I use P for it, I don't know why, but that's what I did, so we'll do it again. So example, oh man, did I not number this example? This was example what?
6.
Thank you.
Or actually 5.
Oh, okay. 5 it is. Example 6 then. So here I define P to be x, y, z such that x squared plus y squared equals to 1. And I'm going to let v plus be x, y, z in P such that y is greater than 0. I'm going to let v minus be x, y, z in P, y less than 0. I'm going to let VR be x, y, z in P, x greater than 0. And I'm going to let VL be x, y, z in P, x less than 0. This should be somewhat familiar. Now the difference here is that we're in three-dimensional space, right? And so what we're going to do, it's pretty simple. We're just going to let the z ride along. And we're going to use exactly what we just did for the circle to construct coordinate charts here. So we're going to do like chi plus of x, y, z is, let's see here, xz. Chi minus of x, y, z is xz. Chi r of x, y, z is yz. And chi l of x, y, z is also yz. Now the difference between the left and the right and the plus and the minus is more evident when we look at the inverse maps, right? Because the inverse maps, if we write them down in their glory, they will reflect the domain upon which the coordinate chart is constructed. So like this would be x comma square root of 1 minus x squared z. And on the other hand, the minus would be x comma minus the square root of 1 minus x squared z, right? Clearly this is an element of v plus, this is an element of v minus, and you probably can tell me what the formulas are for chi r inverse. What are they?
The formula for y.
Yeah, what do you think the formula is here?
Okay, y, sorry. Yeah, y.
Well, y goes in the middle. I'll do the z.
Okay.
Aha.
Square root of
Right.
1 minus y squared.
1 minus y squared, right?
Yeah.
And if you can do that, you can definitely do this one, right? Slap a minus in there.
Yes. So this is basically like a cylinder and then opening it.
Right, yeah, this is exactly. This is a cylinder.
And we're opening
Yeah. Well, sure, you could think of it that way, I suppose. Yeah, let me see here if I can draw a picture. You know, we've got the circle, right? And we're just essentially like attaching sorry, I'm thinking. That's my x-axis, that's my y-axis. Then the V plus would be like you know, that'd be like V plus. Oh, come on. And V minus would be behind the x-axis, right, back over here. You know.
So I basically not square to where x is between -1 and 1, and y can be because
Oh, okay, yeah, you're saying like V plus, well, rather chi plus of V plus is actually, what was it, what you said?
the R2 where the x coordinate is between -1 and 1.
Let's see here. So it's minus, so -1, 1, Cartesian product, the reals,
Yeah.
right? Yeah. Right. Yeah. Whereas, for example, chi r of VR is the reals. Wait a minute, is that right? No. My bad. Hold on a second. No.
The union of
No. This isn't right. This isn't right. Sorry, that's not right. What I should say is that this is like V plus of example 5 Cartesian product with R. Well, that's still not true.
But the union of the four of those.
What I'm trying to say is this. There we go. That is true. That is true. And I'm sorry, you were saying. Oh, I'm an idiot. So going back to what you already told me, if I hit that, then it sends this to -1 to 1, right? And that's just the reals, right? In other words, what's really going on here is that chi plus of V plus from E5, example 5, right? Cartesian product with the reals is what we're doing is we're doing chi plus from example 5, right? Acting on V plus from example 5, right? Cartesian product with what? With the identity map acting on R, right? Which we're essentially all that's going on here, you can look at this as a prototype of the comment that comes after this example. Namely that if you've got a manifold M and you've got a manifold, M with, say, let's say X as a chart, and we have a manifold N with, let me say X, my bad, U1 chi 1 as a chart, and we've got a manifold N with, say, V1, I need another letter. I'll use a psi for the sake, for something different. With psi